What's the challenge there? The challenge is actually mostly on the computing part, because as you can see during last few years, the amount of data sequences that they are generating every year, they are actually growing exponentially. But from other side, if you look at the capability of today's machine, especially for Neumann architecture, you can see they are not growing exponentially. They're getting better and better, but still compared to the growth on the data, we are still far away to do real-time learning. So what's the challenge? The main challenge is like today's computer are not really good on processing large data because we have like limited memory bandwidths, and also the memory is so large, so we can perform the computation. So their prior work that they try to accelerate genome sequence matching and even alignment problem, but the challenge is that the algorithms we try to accelerate, they are not really memory centric. So even trying to make them faster on computers, we cannot get actual benefit. What we are proposing here, we try to actually perform an algorithm, like kind of algorithm hardware co-design. So let me see. So that we develop a new algorithm, which is more memory centric, so we can do more efficient genome sequence platform. So let's take a look at what is genome sequence matching. So the first step on genome sequence matching is to have like, a really large library, like human reference genome that may have billion pairs. And we have a query, as you can see here. We want to see if the query is available on this really large genome in an exact way, approximate way, or in terms of alignment. So rather than performing this task over the original data, we are actually looking at this problem from memorization perspective. We kind of design new algorithm that it can kind of define this problem from different perspective. Think about it more like a history book you have, right? You're reading a book, a large book, and I'm going to ask you a question. What was like capital of like Brazil, for example? So this large book for us, like, it is this library. We want to memorize this library using some human-like memorization model. Then we query it. We ask, do you remember this specific query or no? Or have you ever seen this query exactly, approximately, or even can you align it with what you memorize? That's how we respond, right? We do some analogy too. So let's see how it works in practice. What is a human memorization model? Specifically, we are using a brain-inspired hyperdimensional computing memorization model. This model is coming from a part of brain with name of cerebellum cortex, which is designed actually to do long-term memorization. When I'm walking, when I'm biking, every step, every decision I make, it is happening based on my prior knowledge in actually my cerebellum cortex. So what is happening? Like all you know, your prior information, it is stored in your cerebellum cortex. And like every time you want to make a decision, you do a search operation in a lookup table, which is your cerebellum, in order to see what's the best decision you can make. So, and as we know, brain is not working on original data. Brain is working over neural activity in high dimensional space. So when you observe a sensory information, it can be visual or any other sense, that information in your brain is like a neural patterns. So we want to see how we can use this memorization model in order to do genome sequence matching. So let's take a look at the problem again. So we had a query, we want to check it with large or really long reference genome. What we do, we are performing a neural encoding method to map this library I have, the book, history book, into high dimensional space. Then I perform memorization over that patterns, and I create a really large library in high dimensional space. We name it hyperdimensional library or HD library. Every hypervector in HD library, it is actually storing 1,000 patterns on original space. So meaning that the information of 1,000 like patterns with length, same length as query, it is on a first hypervector, and so on. So when the query comes, we use the same neural encoding to map it into high dimensional space. And now I'm simplifying this matching to a search operation. Just by performing a simple search operation in hyperspace, I can tell you if the query exists on first 1,000 pattern or no, and also for other hypervectors. So it's highly parallel computational model. So Most of operation we do, so the advantage, most of operation we do in hyperspace, they are bitwise operation and very memory centric. You can see most of them, they are based on search operation. The computation, because the hypervectors in our library, they are like holographic representation, there's no dimension more important than another one. So in fact, this representation is so robust against noise and failure as our brain they are. And also we perform kind of operation over compressed data. So let me show you how it works. Think about, you're getting 1,000 patterns from your original, your reference genome. You try to map every genome, that sequence that you have, into a hypervector. Then finally you memorize it. The memorization part is as simple as bundling vectors together, like adding them together. In hyperspace, adding vectors together, it doesn't generate average. It is a memorization model. Why? Because if you ask question from this hypervector that you memorize, do you remember like the first pattern, second pattern? You are going to get the blue distribution, meaning that your similarity of your memorized hypervector with what you memorize, it is high. But the similarity of memorized hypervector with other word, what you didn't memorize, it is around 0. This is this orange distribution. So this is non-existing pattern. This is existing pattern. So by putting one threshold like T, you can actually tell, I can actually tell you if the query, it exists on the first 1,000 pattern or it doesn't. So we're kind of simplifying and revisiting the problem. So of course, the capacity of this hypervector to memorize, why 1,000 here? Why not 1 million? It depends on dimensionality. It depends on precision of every element. So if I'm storing like, 10,000 vector into memorizing it into a single reference hypervector, my noise and signal are going to have good margin. But as I'm storing more and more information, like 1 million hypervector into one memorized reference library, the margin between what I don't know and what I know is going to decrease. So I'm going to lose information. But as I mentioned, my capacity to memorize in every reference genome, it depends on two factors. What is my dimensionality and what is the precision of every element? So, and that creates actually an interesting trade-off here. So we can go to binary representation. We can make sure our reference libraries, they are 0, 1 element, binary. But in that case, I need to use high dimensional vectors, like 4K to 8K dimension, to have enough capacity to memorize like 10,000 vector. Or I can go to 16-bit precision for every element here in my library, but my dimensionality can be smaller. So which one I should select? So this is exactly the same scenario. So I can do my reference library during similarity search to be fully binary, or I can go with high precision elements. So the query is always binary, remember. The reference library, it can be binary or high precision. So the trade-off is that, I can design both of these approach. The first approach, which is fully binary, we name it Hamming distance search, because the search operation here, similarity between query and every vector, it can be computed by Hamming distance, very simply. The second approach is more like performing dot product operation. And there's a very interesting trade-off here. Which one we should select? It really depends on your platform. So I'm going to show you how we design platform for Hamming-based search and dot product search, and I'm going to discuss about the trade-off here. Let's start with Hamming-based design. The Hamming-based design is like content addressable memory. It's a lookup table, right? I want to store different reference library in different row of a lookup table, and then I can perform search operation between query and every line in parallel, row parallel way. So we have made some changes on content addressable memory to support the search we need. Our search is based on a specific threshold. So what we do, we add actually access transistor to every line to make sure the voltage of a row, it is fixed to VDD. Then depending on mismatches that query can have with every row, they start discharging a row. The more mismatches we have, the higher current is going to pass through access transistor. So I can just put a sense amplifier and just detect it. So I want to see if the discharging current from a specific row I have here, it is passing a threshold or is not passing a threshold. So I don't need high precision sense amplifier here. So the challenge, just the only challenge is that, the sense amplifiers are mixed signal block, like ADC, right? Low precision ADC blocks. They're like current comparator. So they don't scale well with technology. So what we have done, we have actually tried to use multi-bit non-volatile memories in order to design a CAM block that can actually support 3-bit, 4-bit precision on every element. Still, the search is based on Hamming distance, but we can actually use less dimensionality because every bit has more precision now. So this work, like we have been fabricated, this work too is not a part of the ISCA paper, but it's our paper on Nature recently. We have fabricated it using ferroelectric devices, and we show how the search in larger scale, it can happen on non-volatile memory in very accurate way. And some of our experimental data results, it shows that our design, it can be about 2 orders of magnitude faster than existing bioinformatic platform performing the same task. But going back to the same our story, so we can perform search operation in binary space, or we can do it in high precision. In high precision, the library, it has like 32-bit value or 16-bit value. How I can do dot product? One way is to use crossbar array, right? The crossbar arrays, they perform dot product operation. But since my query is binary, I prefer to do it in a better way. Specifically, I don't want to use ADC DAC block because they take a lot of area off chip. So we try to do it in digital way. So based on our prior work and also other architectural work, we can perform vector-based addition in memory. So we can actually store these 2 vectors, you can see this input data, inside 2 columns of memory, like 32-bit values. Then we can sequentially add them using some bitwise operation. Similarly, like, I can continue with third block, you can see third column, I can sequentially add it with the result of first addition, create the next one. As you can see, this is sequential, it's gonna take time, but the advantage is that it is highly parallel. Why? How many vectors I have in my HD library? Maybe I have like million hypervectors. So if I have million hypervectors, you can put like, thousands of memory blocks and perform row parallel addition over all of them. So you're gonna get significant efficiency compared to what GPUs they can do because they don't have enough resources. So again, I have 2 designs, Hamming-based design, search-based, like Brain, Approximate, using sense amplifier, or performing dot product, like digital way I explained. And we have tried, and our framework fully integrated with bioinformatic application. We are running it over realistic application, and like some of these like new data set, like specifically COVID data too. And we are performing tasks like exact matching, approximate matching, and also alignment. So I'm just gonna talk about the trade-off that our designs they have. Like, should I use Hamming-based design, or I should use like, my dot product chip? You can use that, like, this is a specification of our chip, what we have. But as you can see, the Hamming-based design is based on sense amplifier, right? And the sense amplifier that you want to detect the threshold, it is a mixed signal block. It's not gonna scale well with technology. We know mixed signals are still on 65 nanometer. So, but from other side, the dot product engine, it's fully like, digital. So when you compare these 2 together, you can see as technology scales from 45 nanometer to 7 nanometer, we expect our like mixed signal based Hamming distance block to get slower. While the digital based design, which is like dot product, which is not fast on 45 or even 28 nanometer, they're gonna be faster on 7 nanometer or so. And I should clarify that our platform, it is faster on GPU too, but the efficiency we get, like if I'm running my new algorithm on GPU and I compare it with existing bioinformatic application, I'm gonna get a slice improvement. And I'm saying a slice is about 1.6 times on speed up and 5 times on energy efficiency when it's running on GPU. But our design is not actually perfect for GPU because we are actually expanding dimensionality and making it so parallel, GPU cannot get the main benefit. But I can go to some of the architectures like processing in memory, 2 architecture I explained, that they can get the advantage of parallelism we have and memory-centric architecture. So we show if you go to processing and memory design, our design can provide 100 times faster and about 90 times higher energy efficiency compared to GPU, which is kind of verified by our experimental chip too. And also we observed that the Hamming design is better than the dot product engine if you are working on 45 nanometer or 28 nanometer, just because it performs row parallel search and it does more analog computation. So it's faster, but as we show, it doesn't scale well. And the last result I want to show, it's about robustness. So hyperdimensional computing is model of neural activity and human brain. So as our brain, it is robust, our design is robust too. If you're running our algorithm and you have some memory error, the memory error can happen because of any failure, it can happen because of attack, or it can happen because of endurance of memory technology, because you have limited write. You can see even you have significant amount of error, random error on memory, we are not gonna lose much accuracy in our Hamming-based design because the representation, it is holographic. All dimensions, they have same impact on computation. So even if you remove some of the dimension because of noise, the pattern of information is still there. But our dot product is pretty robust too. It's less robust than Hamming distance because it is less holographic, but the existing algorithms are really sensitive to the noise. So in summary, comparing these two designs, we observed that the Hamming-based solution, it can be very fast and efficient solution, but it has a scalability issue. So if you're going to deep nanoscale technology, it's better to use some dot product engine. But for dot product, we should try to use less precision elements, like to make sure that we have higher robustness to the noise that we may have in future technologies. So I would like to thank our sponsors who kindly supported our research. And now I'm happy to take your questions. Thank you.
Hi, thank you for the talk. I'm Kylie Huck from LBL, and I also work on hyperdimensional computing. I'm really curious about the projection function that you guys use for mapping the genomes to hypervectors, and also for what the size of your item memory was.
That's a good question. So we are using, the mapping, it depends on the task you do. If you're doing exact matching, we are using some kind of hyperdimensional encoding, which are exclusive. So I'm not sure if other people, they understand, but you should understand. So we want to make sure if you're actually mapping a pattern to high dimension, two patterns that they have even 1 digit different, they need to go to different data point in hyperspace. But when I'm gonna do approximate matching, I want to make sure I keep similarity. So my neural encoding, it need to preserve even one distance between these two. So in our paper here, we explain how we encode for approximate match. But more interesting part is how we do alignment, because alignment need to take care of insertion and deletion. That's actually a relation of our encoding, neural encoding, to kernel method, that we can make sure we can actually take care of position change too. So it has been explained partially on a paper, but we will be open sourcing our library.
Thank you. I'll read the paper.
Mm-hmm.
Any other questions? If not, I have a question. So the solution with Hamming distance, is it basically a kind of binary? Are you basically doing a binary embedding of a string of a length into, right?
True. There are binary vectors that they may have 1,000 or even 10,000 dimension. They are stored in a lookup table, like content addressable memory. I have a query, but I don't want to do exact match, right? I want to see if my search between query and one of these hypervector, the similarity is passing a threshold, that T I show. So it is like exact match, but matching is not exact, is more than a threshold. So that's why we need sensitivity.
What I don't find quite intuitive is once you do this what you call neural encoding, right? Once you do this, I think you solve a lot of problems and you create a lot of parallelism, because you can actually query that against every single item in the database in parallel, right? So I don't understand why is the parallelism in GPU not enough for that? Yeah. So, and are you going for some extra parallelism, and are you seeing some kind of diminishing returns in there?
I can easily explain it, right? Think about if you look at how many cores in GPU you have 4,000 cores in today's GPU, right? So is 4,000 core enough for me to accelerate a library that has billion pairs? Not really. So like, if you're running existing algorithm, the challenge is memory. You have a large memory that store your reference genome, billion pairs, and you have like a small processor or GPU, 4,000 core. But you bring this data all the time to do computation, limited parallelism. So if you want to accelerate existing algorithm, you can go to processing in memory and enjoy parallelism that PIM platform in memory computing it provide. But the algorithms, they don't parallelize. You know, there's a lot of dependency. You cannot get maximum advantage from your existing algorithms. What we do, we try to project it into hyperspace such that the computation becomes, it has less dependency. So we can do highly parallel computation. Now it actually very perfectly matched the processing in memory architecture. But again, we can run our algorithm on a GPU. You're still getting efficiency compared to existing platform. But as we expect, the efficiencies are not much because the level of parallelism are limited on GPU.
Okay. Let's thank the speaker. And next up, we have Leonid Yavitz from Bar-Ilan University in Tel Aviv. Leonid is going to tell us about added distance tolerant approximate matching content addressable memory. So we are still in this DNA world.
All right.
The link, audio, and share this screen.
No audio, right. No video as well. Of course, that's the one, yeah. Okay. I hope you can hear me. Is it working? Okay, very nice. Okay, so hi everybody. Thank you for staying with us. The paper name is Edit Distance Tolerant Approximate Matching Content Addressable Memory. Content addressable memory is the same as associative memory, of which we heard in the previous talk. My co-authors are Robert Hanhan, who is sitting there, and Zhuowen from Technion in Israel, Esteban Garzon and Marco Lanuzza from University of Calabria in Italy, Adam Timan and myself, Leonid Yavitz from Bar-Ilan University, also in Israel. First, let me start with the motivation. I mean, we're living in very interesting time. where COVID pandemic has put our entire infrastructure through some extreme experience. The good news are that we do have diagnostics, basic tests, which tell you if you're sick or not. The bad news are that those tests, PCR or antigen-based, they are not sensitive enough to tell apart the mutations and variants. So for example, with PCR testing, variants like Delta or Omicron would go unnoticed. What do? The solution to this is genome sequencing and genome analysis. Those are the ultimate tools which allow us to control the pandemic, the sharpest lens through which one can understand, track, and again, control the pandemic. The problem, well, it's not the problem, that's the fact that true understanding of pandemic requires what is called pangenomic analysis of every new sequence sample. Pangenomic means analyzing a sequence sample, a genome sample in a context of all genomes of the same organisms which have been sequenced before. Now, the problem is that even with 100K pangenomic context, it takes more than 1 day on a high-performance computer to perform such analysis. To date, we already have more than 11 million of those SARS-CoV-2, that's the name of the virus behind the COVID-19 pandemic. We have more than 11 million already sequenced. So analyzing every new one in such a pangenomic context is extremely difficult. Now imagine this not far-fetched scenario. In a few short years, the world is again plagued by a new viral pandemic. We test 100 million people in the world daily, out of which 10 million people test positive. And since our sequencing technology is going to continue developing, and we will have matured even further, we will sequence 1, maybe 2 millions of those genomes per day. This will create a pangenomic context of tens or maybe hundreds of millions of genomes, making the pangenomic analysis pretty much an intractable problem. So now let's look at the process, which, the process of sequencing and analysis, which happens in 3 stages, again, simplistically. The first stage is to acquire a sample. That could be a sample from a human patient, a spot sample, or it could be an environmental sample, for example, a wastewater sample. In both cases, the samples are likely gonna be metagenomic, meaning there's gonna be many different organisms presented in those samples. The second phase is sequencing. Again, we heard about sequencing in those sessions, but informally, sequencing takes a chemical compound and translate it into a digital representation, which can be processed by computers. The third phase is basically the analysis. Now, EDAM is not attempting to resolve the whole analysis problem. We're looking at the first step, probably pretty computationally intensive, which is detection and classification. Detection means we're trying to understand if the genome that we're looking for, we call it a reference genome, is there in the sample. Classification means we're trying to understand which specific organisms are present in a sample. Now, there are existing state-of-the-art solutions to that. The first one uses exact matching, and those are software tools such as Kraken or Clark. And there is another solution which uses a Hamming distance tolerant approximate matching solutions such as HDCAM. And there is the proposed solution EDAM. Let's look at the exact matching first and why it's not really working. So the problem is that DNA sequence comes with two types of errors, rather edits. The first one is sequencing errors, which come from the sequencing process, and those we want to ignore. We don't want them to affect our decision. The second source are the mutations, which are the legitimate variations between different genomes. Now, those we want to keep. We want to take a deeper look at those. But the result is that when we do exact matching, when we match all those DNA fragments which come out of sequencing process to the database or several databases of several reference organisms, the DNA reads which come with those mutations, they're likely to be discarded by the classifier, not necessarily, but it might happen, which may lead to missing the entire new lineage. And then there is the second kind, which is Hamming distance tolerant solution, which is also, which efficiency is also limited for the reason that DNA, the edits in DNA, they are not only of the replacement type, they are also of insertion and deletion type, which were also discussed in previous talks. Insertion means inserting a base pair or several base pairs in otherwise identical sequences, and deletion is the other way around. So there is an example here, two identical sequences, each of 12 base pairs. So both Hamming distance and edit distance is 0. Now with one single edit insertion of this C element, C base pair, we create the Hamming distance of 12, which is the length of the sequence. And this tells you that tolerating a small Hamming distance, which is typically 2 to 4 bits, which means 1 or 2 base pairs, that's not going to work. So the idea is to create a solution which tolerates edit distance with a programmable threshold to allow us to ignore the sequencing errors. EDAM uses two very simple, very intuitive principles. The first principle, unlike Hamming distance tolerant solutions, we're not looking at collocated sample only, we're also looking at its right and left neighbor. So in this example, 3 top examples actually, there is a chance for a match because of matches with the neighbors. And only in the bottom example, there's no chance for a match, so it's a definite mismatch. Now on the right side, you can see the EDAM cell. And I'm sure you immediately see the similarity, right, between the picture in the center and the right side, right? So here you have those 2 SRAM cells to store the base pair. And all those NMOS transistors, these are XOR elements. And there is this little transistor here, which is responsible for the second trick. This transistor allows us to control the discharge speed of the match line. Match line is a thing of associative memories. And by controlling the discharge speed of the match line, we're able to set a user programmable threshold, which will allow us to control the edit distance. In terms of architecture, in the core of EDAM architecture is the associative array. We take the reference genome or several references genomes, and we chunk them into DNA fragments. We cut them into fragments of certain length, and we place them offline before the operation in this memory, a chunk per line. During the operation, the sample is sequenced, and those sets of DNA reads are streamed into EDAM, where every DNA fragment is compared against the entire database, which contains one or several reference genomes in a single cycle. And on the left side here, we have a counter which counts the matches. So if enough DNA fragments match, if the number of matches exceeds certain user programmable threshold, we decide that the classification is positive, otherwise it's negative. This is how it works. In terms of evaluation, so we focus on two parameters or two criteria. The first one is sensitivity, and the second one is precision. To remind you, sensitivity is the ratio of true positive results to the true positive plus false negative results. Precision is the ratio of true positive results to all positive results, including false positive results. You want both the sensitivity and precision to be as high as possible, as close to 100% as possible, because high sensitivity means you are not losing true results by declaring them false negative, and high precision means you are not letting false results in. So on the left side, you have a graph, a diagram, which presents the results for a low error rate reads, where the error rate is about 4%, replacements, and insertions and deletions. And on the right side, that's the high error rate, which resembles the third generation sequencers. And the error rate reached there at 15%. 1% replacement, 7% indels, 7% insertion, 7% deletions. So, and on the x-axis, that's the threshold. So 1 means 1 edit distance, 2 means 2 edit, the edit distance of 2, and so on. The baseline for comparison is a classifier called Kraken-2, which uses exact search, exact matching. Obviously, it does not depend on the threshold, so those are straight lines. So at the bottom, you see the sensitivity of Kraken, which is about 40%, a little higher. And then precision of Kraken is almost 100%. And this line represents F1 score. F1 score is the harmonic mean of sensitivity and precision. So F1 score of Kraken-2 is about 60%. For EDAM, the sensitivity grows with the threshold because the percentage of false negative results is dropping all the time. That's the this line. At the same time, precision, that's the green line, is dropping because as you reduce the false negative, the false positives actually grow. And the F1 score, which is the red curve, it has a distinct optima around threshold of 3 and 4. And on the right side, that's the result of high error rate. The sensitivity and F1 score of Kraken is around 5%. The precision is 100%. And for EDAM, the sensitivity grows steadily to reach almost 100% at the threshold of 12. The precision, that's the green line, drops to around 50%. So again, F1 score shows a clear maximum around the distance threshold of 10. In terms of performance, if we simulate EDAM at 667 megahertz and the chunk size, the K-mer size is 64, then it outperforms Kraken-2 by 1200x when Kraken is running on Intel Core i9. And on the right side, you can see the physical results of our design, 65 nanometers, 33 square millimeters. It's a big design. The cell is not very dense. And actually, this is it. Thank you.
Do we have any questions? So I have one question regarding, so this ADAM threshold of say 3, what it exactly means that you're looking for matches within added distance of 3,
That's the plan.
right? So what I wonder, does it happen that your system recognizes, let's say, recognizes those that are, let's say, added distance, does not recognize, let's say, those that are added distance of 2 away from the query, but recognizes some that are at a distance 5, let's say, because of the underlying mechanics of how you do this.
So that would be, I mean, depending of which fragment there is, it's going to be a false result. So it's going to be either false positive or false negative. That's why we don't reach 100% ever or almost ever. I hope I understand the question.
So the question is more because when you do this in hardware eventually, do you get some error patterns? Does your hardware actually result in certain error patterns where let's say, it fails to find a string that is at a distance 2 away, let's say that is within the at a distance ball, but find some others that are
right. So yeah, I think I understand. So if you have, for example, a sequence where there is a insertion or a deletion of multiple base pairs, then you are likely to miss that. Yes. But if there is a single indel, you will catch that. According to our analysis, that's where most reads come from.
So I guess there is some limitations in how you manage added distance, right?
Yes.
I guess.
Yes.
Reasonable. If there are no other questions, let's thank the speaker.
Thank you very much.
And the last talk for today, very interesting title. I thought it was a typo, but it's not. Increasing Ising machine capacity with multi-chip architectures, from Anshujit Sharma, who comes from the University of Rochester. He's a 4th year PhD student. So he's going to tell us about increasing Ising machine capacity with multi-chip architectures.
Yeah, I'm already in the.
Okay.
Hello. Am I audible? Okay. Let's see if this works. Oh. Okay. Hi. I'm Anshujit. I'm going to talk about my paper here, increasing async machine capacity with multi-chip architectures. So let's look at what motivated us to do this. So first we need to understand what is this async model and what are async machines. So this async model lets us compute the energy of a system given the spins and the pairwise couplings. However, the optimization problem is that given these parameters, we need to find a state that minimizes this async energy. Hence, these are called async model optimization problems. And all NP-complete problems have their respective async formula. Now, simulated annealing is a common software approach to solve this. However, to mimic one spin flip, it requires hundreds of thousands of instructions in software. But if doing the same thing embodied on a hardware may take as little as few picoseconds. So there is a huge potential for speed up. As a result, people have come up with many different physical embodiments of this annealing process. These are called Ising machines. Now, I won't have time to cover all of this. In fact, there are university courses that explains these principles and practices of these machines. For the purpose of this talk, just consider them as black box extreme accelerators for a very narrow type of optimization problems. So now what happens when the problem size is bigger than the machine? In that case, people go for a partitioning strategy. And the naive approach is to map whatever the hardware can map and leave the rest to software. In fact, D-Wave already provides a tool to do this, but there is a catch. So let's look at the impact on performance. Over here is a speed up versus graph size plot where speed up is in log scale. We simulate a particular Ising machine with 500 nodes chip capacity. In that case, if you follow the plot, as problem size increases, we see that the speed up also increases, which is a good thing. However, as the problem size gets bigger than the machine, we observe this sharp drop in speed up. This part of the graph is also magnified on the right-hand side. Now, is this due to some bad algorithm? Well, maybe. So we came up with our own, which is only slightly better if you look at the blue plot. So this sharp drop in speed up still persists. Why is this the case? So the details are in the paper, but I can give you a gist. So the Ising energy can be best viewed in this matrix vector format. While each of the partitions get mapped to their respective machines, we are left with this gray part over here. These are cross terms that glues the two partitions. Now, these terms can amount to a lot of computation. And if we cannot map this entire matrix to the machine, then these terms will be more and more, and we quickly hit the Amdahl's law bottleneck. So the takeaways are that a nice software hardware partitioning strategy is going to be quickly limited by Amdahl's law. So hence, to maintain a high speed up, we need sufficient hardware capacity. However, we know that capacity of a single device is finite. Hence, we are interested in a multiprocessor architecture, such that multiple processors can collaborate to solve a bigger problem. Now, all of this seems trivial, but as we will see, there are quite a bit of engineering challenges. So from now on, I'll assume one of the Ising baseline, which is this bistable, resistively coupled Ising machine, or BRIM in short. BRIM has capacitors as the nodes and programmable resistors as the coupling units. So the Ising spins get mapped to the respective nodes, and the coupling matrix. The resistance of each coupling unit is inversely proportional to the coupling strength. And note that an n-node graph would require maximum n square number of coupling units. So we will combine multiple BRIM chips such that the glue computation is no longer required. Now over here is an example of a 2x2 array of BRIM chips. And if you already see that it has 36, which means it can map a 6-node graph like this. However, we need some reconfigurable switches to get this to work, such that nodes only on the left column chips are enabled and rest of the nodes are disabled. To summarize, this macro chip architecture helped us remove glue computation. However, it does come with its own drawbacks. Being completely analog, the chip-to-board interface poses an engineering challenge. And the fast-changing analog signals also makes it very difficult to analyze the system. So hence, what we need is actually a digital interface to connect these chips. So our main goal is to build this huge chip using smaller chips. A natural way to partition is something like this. This is, in fact, what macro chip did. However, with a digital interconnect, A better way to partition is to do column slices like this. This way, we only have to communicate the state of the spins between the chips instead of something else that's more difficult to communicate. With this, our logical chips will look something like this. And for the system to work, we need some extra nodes called shadow copies to retain the state communicated from the other chips. With this design, each chip contains the entire global state, but the spins stored in the shadow copies are a little out of date. Now, the shadow copies go for just a minimal overhead because the chip area is dominated by the coupling units. So together with with these chips, if we have a communication fabric, we can already see that this system should work. We can do a rough order calculation of how much actually communication bandwidth is required. So for example, if we have a really large problem and we want to map to multiple chips, it turns out that the total communication bandwidth is greater than 50 terabits per second. That's massive. Why is that the case? Well, we can do the same thing in software and it will require the same amount of communication. But remember, async machines are extremely fast accelerators. So the same amount of communication is compressed in a much shorter time. So we have this problem now. What can we do about it? Well, one thing we can do is to not communicate instantaneously. So instead, communicate the state change after some operating period we call as an epoch. Now let's see why this is helpful. Over here is an example of 3 nodes with their respective spins. And as time goes by, the system will evolve. So let's say that the 3rd node flipped. This keeps going on. And let's say in this entire epoch, there were total 3 flips. However, if you compare the first state and the last state, there was actually only 1 flip that happened. We call this the bit change. And this is what we actually have to communicate. Naturally, a question comes to our mind. Why not wait for a very long time? What's the problem with that? Well, the problem is that we will lose solution quality. Why? Well, if we do not communicate these bit changes frequently enough, then the other processors would be in large ignorance of the true global state. Now, let's look at a plot to understand why this is the case. Let's say we have multiple processors collaborating to solve a bigger problem. And we repeat this experiment with different epoch sizes. So with a large epoch, whenever the processors communicate, they realize they have large ignorance. Now to focus on the qualitative message, I'm ignoring the units here. And because of the large ignorance, each processor mistakes the energy of its current state. So when it gets updated of the other spins, there is an energy surprise, meaning that the true energy of the global state is in fact much higher. So in this scenario, it is very hard to find a good solution. However, if we reduce the epoch size, then this problem becomes less severe until we hit an interesting point where there is a phase change. The values are so small that we actually have to magnify near 0. And if you notice here, the energy surprise is not only the small, it is no longer uniformly negative. This means that some ignorance led us to a solution that is better than we thought they were. So to summarize, we can get away with some ignorance, but not a lot. Now with this information, how can we actually operate our multiprocessors? Here is a timing diagram of one such approach, where each chip is running in parallel for an epoch. We let them synchronize and continue on like this. We call this the concurrent mode. Keep in mind that this synchronization time is largely dependent on its communication fabric. So if you have a low bandwidth fabric, then the synchronization time can be much longer. And in this case, communication becomes the bottleneck. So what can we do about it? We can do one thing where we can have a very large epoch to reduce this demand. But remember, that will cause a lot of ignorance. So instead, what we can do is to run each chip sequentially, something like this. Why? This actually removes ignorance. And the reason is that each chip is updated of the true global state before it starts an epoch. However, because this is completely sequential, we do not improve latency, but we can still improve its throughput. Here's how. We can allow another chip to solve an independent run of the same problem with some different initial conditions. We can do this because e-sync machines are inherently stochastic. So we have to run this multiple times, get a distribution, and pick the best result from that. So this way we can keep all the chips busy at all times. We call this the batch mode. Now we can look at how much actually batch mode can save communication bandwidth. So over here is a plot where the y-axis is the average flips per bit changes, and the x-axis is the epoch size. And we can see that with a very large epoch, we can save a significant amount of communication bandwidth. Now with all of these insights, we want to see how well our multiprocessor architecture works. To do that, we first need to see what a single chip can do, and then move on to the multi-chip version. In this regard, we consider a 2,000 node chip capacity, which is a reasonable size, and we solve one of the NP complete problems, that is max cut, for this K2000 graph. So over here is a plot where the y-axis is the max cut, the x-axis is the execution time in seconds. This is, remember, this is in log scale. And these are the results for simulated annealing. And the dashed line in the middle is the average of those runs, and the shaded region is the range of solutions that we get. So this data is taken from 100 runs. And this horizontal dashed line is the best known solution for this graph. And over here are the solutions for a single chip BRIM. All of BRIM's results are simulated by solving an ordinary differential equation using fourth order Runge-Kutta method. And we can already see that BRIM has extraordinary speed up compared to software. And these are some of the results of other state-of-the-art machines that are out there. The key point to take away is that single chip BRIM has extreme speed up compared to any other solutions that's out there. But remember, when the problem size is bigger than the machine, we get that precipitous drop in speed up, right? So let's see what happens when we implement our ideas into building this multiprocessor architecture. So we do the same exercise of solving max cut, but for a much larger graph with over 16,000 nodes and 134 million edges. We have a similar plot here, but this time we will only show the best results. Results of simulated annealing are over here. And here are the results for a 4-chip multiprocessor BRIM that is 3D integrated, so it has sufficient communication bandwidth and is running in concurrent mode. And we can see that it has orders of magnitude speed up compared to software. It is also quite a bit faster than another state-of-the-art computational accelerator. However, when the communication bandwidth is more limited, as in these two cases, the system will run slower. In this case, our batch mode is actually much more helpful. So with batch mode, the curves move towards the left, indicating that these are quite a bit faster than concurrent mode for the same communication fabric. So to conclude my talk, when problem size is beyond the capacity of an e-sync machine, a naive partitioning strategy doesn't work. So hence we proposed a multiprocessor BRIM architecture that solves this scalability problem. And along the way, we came up with different optimization techniques. For example, batch mode that can reduce a significant amount of communication bandwidth. Another optimization technique we did not discuss here that also saves some non-trivial amount of communication bandwidth. Together with all of these, we were able to maintain extremely high speed up that we hope for. So this concludes my talk. Thank you. You can take questions.
Do you have any questions? If not, I have a quick question, maybe a bit ignorant.
Sure.
So Fujitsu, I think, has some kind of a annealing chip.
Yeah, it's a
For-
digital annealer chip.
Digital annealer.
Yes.
I guess it's somehow related. Does the same problem exist
so,
there?
Yeah, so let me see if I can get to one of the. So a faster version of the digital annealer we have already compared in this plot. So this one, Statica. So this machine over here
I see.
is a faster, it's a more advanced version of that digital annealer. And yes, it's still, it's not technically an e-sync machine because it still uses von Neumann like architecture, like FPGA board, etc., to compute the e-sync formula. So to reach the speeds of BRIM, it still requires to do several orders of flops improvement. So that's the thing.
Thank you.
Sure.
Well, if there's no more questions, then let's thank the speaker again. And that's the end of the session. Please check the announcements about the excursion. So there's going to be buses at 5, 5:40, and I think 6:20. And it's suggested that you actually walk to the destination.